Okay, welcome back to class. This is Friday. The weekend's almost ready to start, July 17th. Finishing up chapter 22 today. So homework 7 is due tonight. And then don't forget, next Monday, July 20th, is test 2 over chapters 19 to 22. So we have the carboxylic acids, we have the reduction oxidation chapter, and then we have all those nucleophiles there in 20 and 21. And then 22 are carboxylic acid derivatives. Sample test 2 is on Learning Suite. We'll have time the second hour today to go through that a little bit. And of course, you can zoom in and we can help you out with that. Chapter 23 then will start also on Monday. Sorry, no rest for the weary there. So got a lot to do on Monday there. I'd like to start out with a little review of esters. Remember, we left off last time with esters, and esters can be made from the carboxylic acid and corresponding alcohol. So R prime can be the same or different, of course. And then acid catalysis. We call this the Fischer esterification. We went through that. It's a reversible process. If you have water and acid, you can go back to the starting acid and alcohol. You can also make this with DCC and leave out the acid catalyst, right? And so that way you can do it at 1-to-1 stoichiometry under neutral conditions. Now today we're going to do this. We're going to hydrolyze or break apart the ester with water with acid conditions. And that's going to give us back the carboxylic acid and the alcohol. Or you can do it with base, sodium hydroxide. And this is going to be called saponification. Saponification is an archaic term that relates to soap. In fact, this process using the acyl triglyceride or fat, we're going to mention that, is how soap was actually discovered by the ancient Romans. So the cleaning action, the micelle action, comes out of the base mediated hydrolysis of esters. And it actually gives a different product. And you need to pay attention to this because it gives the sodium salt of the carboxylic acid. You're under basic condition. It also gives the alcohol, but look, it's a different product, okay? This is the sodium carboxylate. This is the neutral carboxylic acid found under acidic conditions. They're actually two different products. This one is actually soap, okay? This one's not, okay? So here's the stuff in nature. If it's saturated here, these are long chain C16 through 18. That's palmitate and stearate esters, very long chain fatty esters. And this is from glycerin. So these are called acyl triglycerides. So this is fat. Saturated fat is lard. That's a solid at room temperature. If it's unsaturated, there's some double bonds here in this long chain R group, unsaturated. It can be polyunsaturated as well. These are oils, and they're liquids at room temperature, okay? So we can treat those under saponification conditions with sodium hydroxide water and make what? Glycerol or glycerin, the tri-ol here of propane, and 3 equivalents then of the sodium carboxylate are liberated. All right, let's go through each mechanism here. And again, you're probably bored by these mechanisms because they all involve the same thing, tetrahedral intermediate and then a nucleophile coming in. But it's the variations in the conditions. What you need to be careful here with the esters is if you're under acidic conditions, you get the neutral acid. Basic conditions, you get the carboxylate, salt. Okay, let's do the acid one first, I think. See what the mechanism's going to be there. So let's take, just ethyl acetate and treat it with water and acid. And this can be catalytic sulfuric acid. Okay, how do we start it out? Let's go ahead and protonate the carbonyl. And once we have the protonated carbonyl, then we're more susceptible to attack by water, you see. We've made the electrophile more reactive there. First couple steps, And that goes directly to that. And what hydronium ion here? And if you've noticed, this is the exact reverse of Fischer esterification. Okay. If you practice that, hopefully, you'll see how easy this is. We need two there, right? Okay. Now we can transfer the hydrogens, the protons in an intramolecular manner. That's okay. Or you can take this off with solvent, which is water, and then put it back on the ethoxide group. We've got to get rid of the ethoxide, right? So what do we get here? We get the ethoxide protonated. It's now the hydronium. The alcohol is now neutral here. And now we can bring a pair of electrons down and kick this off. Now I could have pulled off ethanol on its own and had a carbocation here. That's okay, I'm just using the lone pair to go directly to the carbonyl. It's the same thing, really. It's just the resonance structure of it. That and the alcohol. Well, there's one of our products. Okay. How do we get the carboxylic acid? We are under acidic conditions. What we have here is water. It's definitely our base in this case. So there's our two products generated from the acid catalyzed hydrolysis. And what does that term hydrolysis mean? Lysis means to break, and to break with water. Okay, so we're using water, it's a solvent in this case, to break that ester back apart. Okay. Now let's look at the saponification mechanism, which is really the same thing. We're breaking the ester apart, but we're doing it under different conditions. So we need to be a little bit careful about this. Let's do a different ester here. How about methyl isobutyrate? That'd be a common, we'd call this what? Methyl 2-methyl propanoate for the IUPAC name. Okay, sodium hydroxide and water. Now, what is our nucleophile? Well, of course, it's hydroxide, and that directly attacks. We're not protonating the carbonyl now, right? Because we're under basic conditions. We don't have enough proton strength. Okay, so we're down here at pH 12 or 13 or 14, whatever. Okay, 14 would be one full equivalent, 1 molar sodium hydroxide. Very, very aggressive reagent. But let's use that as a nucleophile to attack there. So we get O minus, OH, and OMe. Okay. This mechanism is actually quite a bit simpler. Again, this is the saponification reaction. Sapone or sabone, I think is the Latin term for soap. It comes from ancient Rome. Not the Spanish term. Sapo in Spanish means toad. I guess you could make soap out of a toad if you had enough fat in him. I don't know. But saponification is the archaic term. It's still used, though. Base-mediated hydrolysis of esters. So we get to this point. Let's break it down. Tetrahedral intermediate. What do we get here? Oh, we get the carboxylic acid. And we get OMe minus. Are we done? No, this is basic conditions. This carboxylic acid is not going to hang around. This is methoxide in the presence of water. And yeah, with base here, this will be deprotonated to some extent, but equilibrium-wise, there's a lot more water around, okay? In fact, you can use this, right, as the base here. Let's just go ahead and do that. And what do you get? The actual product for saponification is the carboxylate salt and the neutral alcohol, okay, because that's basic enough to take that proton off. And where's the other cation? Well, the sodium cation goes along for the ride. So that's your product, again, for saponification, for forming that. Let's look at a little bit of mechanistic evidence here. There's a lot of other mechanisms that were initially proposed for these types of reactions. Part of the evidence here is the rate of this reaction directly depends through a rate constant on the concentration of the ester, starting material, and the amount of hydroxide. Which means what? Looking at our mechanism, so it's bimolecular. These two concentrations affect the overall observed rate. So what's the slow step here? Well, it's one involving both of these. So you'd say this is our slow step right here. Breakdown of the tetrahedral intermediate, you would say, would be fast. Okay? So that's consistent with that data. Another thing is stereochemistry. Let's look at an ester where we have a stereocenter. So here's a ester with a stereocenter right here, this methyl group, and this is a secondary position on this ester. And what is that stereocenter? Let's see, it's S. Okay. Now let's go ahead and do the reaction here. Let's saponify this ester right here. Sodium hydroxide, water. And what do we get? Well, we get benzoate, sodium benzoate, and we get the alcohol. Now, what happened to the stereocenter here? Well, it's retained. You can actually observe that, and these optical rotations are known for both the R and the S. And this one was found to still be the S, okay? So the mechanism does not involve this pathway, direct attack here, and loss of the ester as a leaving group, right? Because that would invert that and give, instead of the S, I'd give the R. So a little bit about the mechanism. This clearly shows it's not that approach there, okay? So let's say no there. The approach is here, okay? And that goes directly there. So a little bit of evidence. The molecularity of the reaction, okay, the overall kinetics that you can see coming out of that from the rate, depending on both the nucleophile and the ester. And then the stereochemistry going with retention of that stereochemistry, okay? So I think that's a good couple of things to keep in mind there. One other thing on the acyl triglycerides. So here we've got our stuff that we can get out of animals or plants. We can get animal lard, beef tallow, whatever, the marbling you see in steaks or roasts, whatever. That fat can be rendered out. That's an acyl triglyceride, okay? If it's fully saturated, it will be a solid at room temperature, or it can be a liquid here. Now, what we can do with this is not just saponify this or hydrolyze it with acid base. Let's take methanol or ethanol here, okay, and use a simple base, potassium carbonate, okay, and we're going to do what's called a transesterification. Transesterification reaction. What does that mean? Transfer one ester to another. So here we have the acyl triglyceride from the animal or the plant. We're going to form what? We're going to form glycerol. The leaving group comes off like before, but instead of forming the carboxylate things, we're going to form the methyl esters. Okay. And these long chain methyl esters actually have the same boiling point as fossil fuel diesel. So what can be used here? This is a renewable source called biodiesel, where we can convert plant oils or animal fats directly into a fuel that can go right into a diesel truck or a diesel car engine. Europe has many more of these. Audi and BMW have these smaller cars that run on diesel fuel, and that can be renewable, right? This is a non-fossil fuel now that can be renewable. You get three equivalents out here. There's a little bit of processing that needs to go on, but the boiling point here is about like normal diesel fuel, which is the C14 to C18 cut of the hydrocarbon that's distilled out of a barrel of oil. But this diesel fuel comes directly from a transesterification reaction there. It can be renewable that way. Okay, let's look at a couple other polyesters briefly. This is a triester, of course. Let's look at one where we've got an ester from an aromatic carboxylic acid. In fact, this one has two carboxylic acids. This is called terephthalate. Terephthalic acid. You can react that with ethylene glycol and acid and heat. Okay, so what are we going to do? Well, it's an alcohol with a carboxylic acid. The acid catalysis, sulfuric acid or HCl, makes what? The polyester. So let's see what that looks like. It's got the terephthalate linkage. Then it forms the esters, you see, with the ethylene glycol here and the benzene rings. I'm not going to draw too many more of them here. Let's see. How about just leaving it off there? There we go. I show enough of the units there. So X can be hundreds or thousands of units long. It's obviously a solid material now. That's PETE, polyethylene terephthalate ester, which can be molded and formed into all sorts of products. It's a very rigid material. It's not very biodegradable. These are aromatic esters. Eventually in nature, they do degrade here, but these both come from petroleum sources, which can be a problem. It's not renewable here. So most polyesters now, or at least a lot of them, are being made from a different acid. Let me show you this one. The new polyesters are made simply from lactic acid. Lactic acid, of course, natural material. It's got a stereocenter. That's the R stereocenter. But if you heat this up with an acid, you can get it to polymerize. This is an alcohol. This is an acid, right? So if you heat this up, what do you get? You get polylactic acid, or PLA. Okay. What does polylactic acid look like? Well, I'll draw some of it here for you. Hopefully, I got enough art skills to do this. That's probably enough. Yeah, okay. There you see the lactic acid units, the esters here, they're secondary positions, right? Notice the retention of stereochemistry because it's R right there. The business end is, of course, protonating here, and then the alcohol adds what? Right there, right? To get the polymerization to go, and then you got to transfer a proton off there or whatever. But this is polylactic acid. It's a solid, rigid material also, and it's nicely biodegradable. And when it degrades, it makes naturally occurring lactic acid. Okay, so there's a solution to the recycling problem that PETE presents. Another thing about esters, I've been mentioning some of the biology. Let's look at how esters are made in biology. They're made from carboxylic acids and ATP at first. Now, what's ATP? Has anybody heard that term before? Yeah, adenosine triphosphate. What is that molecule? Well, it's the energy molecule inside of cells. All living cells have to make ATP. And the ATP made inside of a cell is used within that cell. In higher animals, most ATP is used for muscle contraction and movement. A lot of neuron transmissions also use ATP and other processes in the body, but most of it goes for muscle contraction. But let's look at ATP, and what's the structure? The triphosphate part's what we need to look at. And the phosphates have a lot of charges on them. So these are phosphoric acids that have been condensed here. And and then the rest of this thing is a big adenosine unit, and that's the nucleotide. We're not going to look at the structure of adenosine. I'm bailing out there. I'm just showing the triphosphate part, okay? And what occurs here in nature, there's an enzyme that does this. And within the enzyme, it binds the carboxylic acid you want to make a derivative of, and it binds ATP. So there's a lot that goes on here. But the main thing is taking the proton off here, allowing the phosphate to undergo nucleophilic attack. You have a tetrahedral intermediate again, just like we've been talking about. Bring the electrons back down and kick off ADP. Okay? So what this goes to is this then. It goes to the phosphate now being transferred to the acyl group, okay, plus ADP. Now what's ADP stand for? Adenosine diphosphate. Here's the two phosphates, okay? Now why is nature making this? Well, that's a derivative, again, of a carboxylic acid. And it has a better leaving group on it now. Okay. So let's see, what type of a group can we have here? Well, it depends on what the process is, but a lot of times we use thiols. And this thiol here has an enzyme, of course, associated with it. The enzyme takes the proton off. That allows for this to attack the sulfur nucleophile, tetrahedral intermediate, bring it back down and kick off phosphate, okay? That's a better leaving group. Acyl phosphates are not as reactive as acid chlorides, but they're close, you could say. I mean, a phosphate leaving group is resonance stabilized. It's a better leaving group than an ester, okay? And what it makes here is the Thyle ester, okay? And our group here can be a lot of different things. We'll look at coenzyme A, acetyl coenzyme A, and that'll have a big adenosine. I'll show you the structure in a second, but we're just looking at the functional groups and what's important here, right? Acyl-CoA can react with a number of things, alcohol-wise now. A different thing, tetrahedral minute, come back down, and there you go. There's how the esters are formed in biology. It goes through first an acyl phosphate, then usually an acyl thiol, and thiol esters are more reactive than oxygen esters, and they're formed there. The key one here that's used in biology here is choline, which is this guy. Choline is a trimethyl ammonium ethyl alcohol, and this is used to form acetyl choline. Acetyl choline is responsible for the tensed state of muscles. This is the main neurotransmitter found in muscle tissue. Well, actually, the junction between neurons and muscle tissue. So that's the tense state. In order to relax muscles, there has to be a acetylcholine esterase that hydrolyzes that ester. Okay, and the mechanism follows exactly what we've been talking about. So it's kind of cool. There is also alcohols that need to be transported, like cholesterol, that on their own are not soluble enough. And they're often acylated to actually become less water soluble and then put into an HDL or an LDL, the high density or low density liposaccharides, lipoproteins, sorry, that are used to transport non-polar materials through the blood. Anyway, all this stuff from carboxylic acid, acyl phosphate, acyl thiol, and then to ester. Let's look at the overhead now. Let's go back up here and look at those cofactors briefly here. Is that showing up there? You see that okay, Ruben? Okay. He's given me the nod there. Again, all these graphics you have on Learning Suite, your book just mentions some of these briefly. I like to show a little bit more of the complete story. Here's cofactors you've probably heard of before. In fact, we've mentioned NAD, NADH. This is Mother Nature's reducing agent. This is Mother Nature's oxidizing agent. And the head group here is where all the mechanistic stuff works. Same with FAD, a little less common. FAD is the flavin thing with a tricyclic structure to FADH2 here, adds 2 hydrogens there. This one's important for the electron transport chain, you'll learn about later in biology. But here's acetyl-CoA, the one we were just talking about. And wow, that's a big molecule. Here's the adenosine nucleotide over here with another diphosphate, and then this pantothenic acid unit here, which is kind of a spacer. It has 2 amides in it. The business end's right here. Here's the Thyle ester. And that's made again from the acyl phosphate, and then the sulfur from a CoA unit comes in. And that helps transfer these acyl groups in biology. That's the main way that they're transported. Let's look at this, how this relates to fatty acid synthesis. So these are made from glycerol and the acyl CoA here, or acyl karyoprotein thiols. And so a base can take off this proton, this can attack tetrahedral intermediate, and then the thiol can come off. And it does 3 times there to form the acyl triglyceride. If they're all saturated here, don't worry about the terms, the names of all these. We'll have a lipid chapter later on. We'll review this a little bit. But you see, these are all saturated here. So these R groups can be really long, 16, 18, whatever. They're saturated. Look at the melting point, 70 degrees C. What's the temperature, room temperature in Celsius? Yeah, about 23, 25. Unless you're in Phoenix, it's about 45 degrees Celsius, especially nowadays. Um, so these might be liquids in Phoenix. I don't know. Okay. Maybe in Mumbai also. I don't know. Probably in India, yeah. If they're unsaturated, though, here's polyunsaturated, linoleic, and linolenic has 3. Arachidonic has 4. I'm not showing that one. But look, the melting points are below room temperature, so these are all liquids here. And it's because they don't pack well in the solid state. They have these kinks or bends to them. So the more efficient packing is the straight chain fatty acids. Anyway, enough on that. Speaking of fats, let's show you a little bit about the synthesis. And this gets into a topic coming up in chapter 23, 24, the enolates and enols. And so we're not going to talk about that. But if a base can take a proton off the alpha position, that becomes a nucleophile. Nucleophile can add to another acetyl-CoA group to form a malonate type structure. Or butyrate, yep, butyrate. Butyrate can undergo reduction with NADH. There's the hydride reducing it to the alcohol. That would be an aldol type product. And then you can eliminate water. You get the alpha beta unsaturated Thyle Ester. And then add hydride again. And then you see quench the enolate with a proton. And there's your butyrate, your 4-carbon unit. And that just continues on up, 6, 8, 10, 12. So they're all even numbers in biology. Here we get up to 6, hextanoate, and on up to palmitate and stearate. Those are the saturated ones. I won't show you that. Penicillin, we'll get into that in a minute when we start talking about amides. So let's pause right there on that. Let's go back on the board over here. Sorry, I keep making you move around there. Keeping Ruben on his toes today. Okay. Let's get some more room here. Let's talk about amides. So yeah, we talked a lot about esters. Sorry about that, but amides now are very important. And amides, a couple different ways we can form them. Carboxylic acid and an amine. Now, depends on how you do this. If you do it at room temperature, or you can do it at 100 degrees. And those are the 2 temperature differentials we'll have for the class. The book is kind of unclear on this. Okay, I'm going to say room temperature, and if you just react an amine, ammonia, or whatever amine with a carboxylic acid, what do you get? You get simple acid-base chemistry. All that happens is the amine takes off the proton, you get the ammonium cation or the alkyl ammonium cation, whatever. So you just get acid-base chemistry going on at room temperature. And why is that? Well, an amine is a base, right? And a carboxylic acid is an acid. So, and you can look at the pKa's here. The pK of ammonium is 9. pK of a carboxylic acid is 5. So which side is favored? Yeah, it's highly favored here to the right, forming the weaker acid, okay? You always use the stronger acid to transfer the proton. That's what that means, right? But if you heat this up, there's some other things that you can do here. You can actually drive off an equivalent of water. So we're perturbing the equilibrium. We're adding more energy to the system. And now, because we're generating a water molecule, the entropy is increasing. It's becoming more randomized. And remember, free energy always equals the enthalpy minus T delta S. So it's the energy in bonds and the randomness of a reaction. You make a system more random, you can make it favorable. At 100 degrees, that takes over. And what you can get is indeed the amide, okay, plus a molecule of water. And so this acid-base chemistry is going on all the time. But at higher temperatures, you can begin to get some nucleophilic addition, proton transfers, and eventually formation of water. But I'll be clear about this in class here, right? Room temperature, acid-base chemistry, that's it. Okay. Higher temperature, let's say 100 degrees, just to be clear. Then you can get amide formation cleanly. Okay. The other thing that we'll look at here is taking the amide And reacting that, how? The amide, that's the most stable thing. We can't form anything that's less stable from the amide. And remember, the amide is very stable because of resonance, right? So we've got that resonance effect that's stabilizing and not making the carbonyl very electrophilic, because these electrons are what? Donated toward the carbonyl. So it's the most stable thing we know. So how can we do this? Well, we can take water, and on its own, remember, it takes years for an amide bond to hydrolyze. But if we react it with concentrated acid and water and heat, or hydroxide, the extremes of the pH scale, we need to be down here around pH 1 or 0, or up here at 13 or 14 in order to get this reaction to go. And a lot of times it's still kind of a slow reaction, especially if you have NN dialkyl amides. It can be even slower, but it can go. But you have to have the acid or base. If you leave those out, no reaction just with water. Okay, it's on the geological time scale. It's going to take years to hydrolyze. But if you have the acid or the base, then it can hydrolyze. If we're going to do it under acidic conditions, that's going to be our product. Okay. If we're under basic conditions, it's like saponification. We need to show the carboxylate, sodium salt, plus the neutral amine, okay? Different products, but still cleaving of the nitrogen acyl bond, okay? But be clear about that. Link your product to what those conditions are. And we'll see from the mechanism here what we're talking about. So yeah, let's do the mechanism of a couple of them here, and let's see what we need to get out of that. So let's do, which one should we do first? Oh, how about acid? Acid-mediated amide hydrolysis. And how about if we do ethyl and ethyl amide? So water, sulfuric acid, and heat, okay, in order to get this to go. So what are we going to do here? Yep, protonate carbonyl. So we can get that. Okay. And then what? Water can attack, right? So we can get OH, hydronium ion, NH. Okay. Tetrahedral intermediate again. Nucleophile. Hopefully you've practiced enough of these to see these. We need to turn the nitrogen into a leaving group now. It has a lone pair there, so let's transfer a proton. So what do we get here? We get the ammonium, because we'll have two hydrogens on there now. We still have the ethyl, or whatever's on the nitrogen, right, at that point. There we go. And then what? Bring the pair of electrons down, break open the tetrahedral intermediate, and we get the protonated acid. Okay. And what's our nitrogen at? Well, it's NH2 ethyl. Now, is that the end of the story? No. Why? Because we have a neutral amine here under acidic conditions. That should make you concerned about finishing off the mechanism here. In fact, we have a protonated carboxylic acid. Let's just use that amine to grab that proton there. Now, we could do it, stepwise there, having the solvent water take that off, and then we could have another equivalent of ammonium or hydronium cation protonate the amine. Either way, and what do we get here? The product is NH3 with an ethyl and a plus charge there, okay? So that's acid-mediated amide hydrolysis, okay? Let's see, do we have time to do base? Yeah, I think we're okay on time. Okay, yeah, let's do the base one now. So we just modify this a little bit and see what we can do here. You could pause your video and give that a shot and see what we're gonna get. Yep, and we're back. So the two products are gonna be this. The sodium salt of the carboxylic acid plus what? The neutral amine. Correct. Why? Because we're under basic conditions now. So let's see, how can this work? Well, hydroxide is a good nucleophile. O minus, OH, NH, ethyl. Okay, tetrahedral intermediate again, but using the charged hydroxide as our nucleophile is going to give the O minus here. And then what's the next step? We'll bring the electrons back down and kick off NH minus. Okay, we don't have enough acid to protonate that. And yeah, we have heat here, so you can get this to go. And what do we get? We get the neutral carboxylic acid plus what? Oh, NH, ethyl, 2 pairs of electrons there, so that's a negative charge. We get the amide anion. Now that may look kind of funny, but we are under strong base conditions. This is okay for a while, but is this the end of your mechanism? No. Here we have a carboxylic acid, right? In the presence of a very strong base, right? So what's going to occur here? This is going to grab that proton very quick and give us the sodium carboxylate salt and the neutral amine. Those are your 2 products. Oh, there they are right there. Okay, we already got it. All right, questions on that? Yeah, hopefully that exercise helped you out. Coming back here, the second hour, we'll do nitriles, and we'll do a demonstration with nylon, and we'll talk a little bit about penicillin, and then we'll also get to sample test 2. So let's take a break here, pause for the cause, 10 minutes, and we'll be back. Thank you.